Okay, so we have a whole bunch of pages here. These are all 9.3 interference, paper 2. And so the first one that I'm interested in is actually 1D. So 1D, E, and F. So let's zoom in on those. Because 1A is Doppler effect, 1B is SHM, 1C is, I think, also Doppler effect. But then we can see from our pattern right here that 1D, E, and F involves is it multi-slit? Yeah, 4 parallel slits, 4 slits. So let's go from there. Okay, so this is not 2 slit, this is 4 slit. And then it says the number of slits is increased, but the separation and width of the slits remains the same. It says, now what happens to the angular position of the primary maxima, like where they actually are relative to the center line? And for the 2 slit equation, we have S equals lambda D, capital D over lowercase d, where lowercase d is the separation between the maxima on the screen, and increasing the number of slits really has no bearing on that equation. And then diffraction grading, this looks like it says cliff. There we go, diffraction grading, and lambda equals d sine theta, where d is the width per slit, and then theta is the angular position of the different maxima. That n is just an integral number. The actual slit count itself has no bearing on sine of theta. So increasing the number of slits will have no effect on the angular position. Okay, next question. State what will happen to the width of the primary maxima if you increase the number of slits. And we know that as the slit count increases, while there will be no effect on the angular position of each maxima, the general intensity of the pattern gets brighter. The intensity of the primary maxima does get brighter, but those primary maxima themselves also get more tightly focused. They get narrower. So what will happen to the width of the primary maxima? The primary maxima get narrower as you increase the slit count. But note that it says what will happen to the intensity of the secondary maxima. And if we look at the picture, the secondary maxima are the little tiny maxima in between the primary maxima. And as you increase the slit count, the intensity of the primary maxima increases. So intensity, when I said intensity before it grows, I meant the intensity of the primary, the main maxima, increases. But then it also said that the primary maxima get narrower. What does that mean? That means that the space in between the primary maxima, if the primary maxima are brighter and narrower, that also means that the space between the primary maxima is going to get darker. More of the light is going to the primary maxima than to the secondary maxima. So since the primary maxima are narrowing, I need to squeeze this in here, then the secondary maxima intensity is going to decrease. Probably, if I should pretend like this was an actual answer, I wouldn't use a down arrow, I would use the word decrease. Got to be clear in your answer. All right, and so that is 1D, E, and F. Now let's move on to 2A and B. Okay, we have ourselves a thin film situation, and the thin film is upon a glass sheet. So we're not going from air into the thin film and back out into air like a soap bubble, but this is one of those non-reflective coatings where the thin film is put on a glass sheet. So 2A, state the phase change when a ray is reflected at B. So, pretty basic answer to this one. When light reflects off of a higher index, which with this, in this case, the glass, it says that the end glass has a greater index than the coating does. So yeah, when light reflects off of a higher index, a 180 degree or pi radian phase change occurs. There you go. Next question, 2b. All right, 2b says, explain the condition for W, the width of the coating that eliminates reflection for a particular light wavelength in air, lambda air. So if you want to eliminate the reflection, we want the condition for destructive interference. And so the reference table says destructive interference. The condition, I'm looking at the wrong thing here. Yeah, destructive interference, 2dn is equal to m lambda. But remembering those are the conditions if you have air on both sides of the coating, or if you go from air to coating to a lower index, that's the situation. But we're going from air to coating to higher index. So air to film to glass. So in that case, we know that the constructive and destructive interference equations flip. So the condition for destructive interference in this case is not 2dn equals m lambda, it's m plus 1/2 lambda. And I think it says condition for W that eliminates reflection. So it doesn't say the minimum coating width, just what's the condition for W that the reflection is going to be eliminated. Well, first of all, let's fix this equation. Instead of m lambda, it's m plus 1/2 times lambda. And so the width of the film is integral numbers of m plus 1/2 times the wavelength in air over 2 times the index of that coating. The mark scheme says that they want you to say that it's the same phase change at both boundaries, meaning that the reflection at A has a 180 degree phase change and the reflection at B also has a 180 degree phase change. I feel like we said that in 2A, and I feel like that argument is implied in the use of 2dn equals m plus 1/2 lambda for destructive interference, but I'm just going to write in the phase change bit just to satisfy the mark scheme for all three marks. So that's the same pi radians phase change at the air film boundary and also at the film glass boundary, but that's why I'm using 2dn equals m plus 1/2 lambda for destructive interference, which is the opposite in the data booklet, but the data booklet is set up for air to film back to air or back to a lower index, not the situation here. But that's 2b. All right, let's move on. We don't need 2c or 2d. That has to do with the resolution. That's our next topic after 9.3. So here is number 3. So we're dealing with a diffraction grating here, and it says that this angle theta is pointing at a second order diffraction maximum on the screen. And so we have theta, and we have 3 different slits, X, W, and V, and some triangles here. Incidentally, in terms of the proofs before about theta and figuring out path difference and whatnot, I remember that I had said that that this angle, when we have this angle right here, is the same as this angle right here, which is how we can get the derivation for path difference. But it hadn't dawned on me at the time why that's true, but I finally figured that out. So let me just kind of show you that real quick. All right, so here's the the geometry in question. So we have, this would be the slit side over here. This would be the slits. This would be the screen side over here. And then the not dashed line is the ray of light going from the slits to the screen. And it's talking about path difference. So if I had slit A and B kind of right there, and they each had light coming out of it, it's making reference to the path difference between them. And of course, if it's destructive interference leading to a dark band on the screen, then the path difference would have to be half numbers of wavelengths, integral half numbers, 1/2, 1/2, 2/2, 3/2. because crests would be meeting troughs that have to be completely out of phase. If it leads to a bright band on the screen, that would be max constructive interference, and the path difference would have to be an integral number of whole wavelengths, lambda, 2 lambda, 3 lambda, etc., so that when the waves meet on screen, they are in phase. Crests meet crests, troughs meet troughs. There's no phase difference, and you get max constructive interference. But in order to analyze this, we say that the angle given right here in the diagram is the same as this angle right here, so that we can use a sign, like sine of theta is opposite over hypotenuse, where the opposite side is the path difference. If we want to use that, I think that's a lowercase delta, but that's the path difference symbol, and then the hypotenuse would be the distance between the slits. So like on this side, we'd call that D, the distance between the slits. But my issue is why are those two angles equal to each other? And I just figured that out. So by alternate interior angles, I have three right triangles broken up right here. I have this big right triangle, and I have the tiny one that I'm trying to analyze, and I also have there's a right triangle on the bottom. But these two lines, the dashed line on top and the dashed line on bottom, are parallel to each other. I know that by alternate interior angles, this angle right here, oops, that's not a highlighter. There we go. That angle right there and that angle right there are equal to each other because of alternate interior angles. Also, the complement to those angles, there I can, by alternate interior angle, those two angles are equal to each other. And in order to analyze this triangle right here that I'm interested in, I'm actually looking at this larger triangle right here. And just in terms of the angles that I know, I'm starting off, let's see, I know this angle to start from. That's the angle from the slits to the screen. I know this angle, this second angle, that's 90 degrees. And if I know two angles of a triangle, I now know the third. That would be the complement to the angle, the theta, from the slits to the screen. And by alternate interior angles, I was able to show that, let's see, this guy here is equal to this one here. I also know that this second angle over here is 90 degrees, of course. And so, therefore, if I know this guy and I know this guy, I now know this angle right here. And I'm able to show that this angle is equal to that angle there. Now, why does that matter? It doesn't actually matter for 3A, it does matter for 3B. So anyway, let's knock out 3A. It says state the phase difference between the waves at V and at Y. So if it says that light waves are diffracted through an angle theta to form a second order diffraction maximum. So if we're talking diffraction maximum, so diffraction maximum means that we have constructive interference, so that there is no phase difference. So the phase difference is 0 degrees or 360 degrees, or in terms of radians, it's either 0 radians or 2 pi radians. Then 3b, state in terms of the wavelength, the path length between points x and z. So that path difference. It does say that the diffraction grating is a second order maximum. So using the diffraction grating formula, this is a second order maximum. So n is equal to 2. We have lambda. D, of course, is the slit separation between two adjacent slits in this equation, and then, which is, of course, is also given in the diagram, and then sine of theta, we're talking about, again, this triangle up here, so this guy right here, and it's asking about this xz, why am I using green? Go back to black. This xz segment right there, which is the path difference in question, and my whole thing before was that this angle theta and this angle theta are equal to each other, and so sine of theta is opposite the path difference over the hypotenuse, which is this length right here. And of course, that length, the hypotenuse there of that triangle, xv, is 2 times the slit width. You can see right here, xv is 2d. And so we just simplify. We're looking for delta, we're looking for that path difference. And in the end, when we get delta by itself, or the line segment xv, we wind up with 4 lambda. So the path length between points x and z is 4 lambda. All right, 3c. The separation of the slits is d. Show that for a second order diffraction maximum, 2 lambda equals d sine theta. And 3c, I kind of did 3c in 3b, but just to reiterate, it has to do with what the sine of theta is equal to. So sine in that small triangle that we just analyzed, sine of theta is opposite over hypotenuse, or in terms of the line segments, opposite is xz, and then that hypotenuse is x, line segment xv. We know that xz is 4 lambda, and xv is 2 times the slit width. And so if we rewrite this, multiply both sides by 2d, we get that 4 lambda is 2d over sine theta, and if we divide both sides by 2, we get 2 lambda equals d sine theta. Honestly, I think that 3c should have happened before 3b, but because they kind of do the same thing, but whatever. There we have it. Okay, but we're still on number 3, but now we have a different situation here. We have a nice little graph guy. It says monochromatic light of wavelength 633 nanometers. Normally incident on diffraction grading, the maxima on the screen are detected, theta is determined. Graph shows variation of sine theta with the order n of the maximum. Central order corresponds to n equals 0. I can see from the graph that it's directly proportional, which makes perfect sense. Determine a mean value for the number of slits per millimeter of the grading. Well, first of all, let's take a look at the diffraction grading formula. Ooh, this sucker's 4 marks. Let's go. So we have n lambda equals d sine theta, and so we have sine theta on the y-axis and n on the x-axis. So I'm trying to fit this to the equation of a line. Y equals mx plus b, and I can see that the y-intercept is 0 because this is showing me direct proportionality. So let's rewrite n lambda equals d sine theta. Divide both sides by d to get sine theta by itself. So I wind up that sine theta is lambda over d times n. And so the slope of this plot, so let's see what this slope is. Let's zoom in a little bit. That is definitely at the origin. And then on the other side over here, the line seems to connect with y equals 0.4 and x equals 5. Right here. Right there. So going down, oh wow, that's terrible. Going down. Pen, hello, pen, here we go, pen. And x equals 5, and for y equals 0.4. When figuring slope, you need to make sound effects when determining points. So rise over run would be 0.4 over 5. And it's also a unitless graph, interestingly enough. So it'd be a unitless slope. There's also only one significant figure, which is strange. But anyway, the slope is 0.08. We do know the wavelength. And so it says, what are we looking for? The number of slits per millimeter. Well, D doesn't give us slits per millimeter, but it does give us the width of the spacing between 2 adjacent slits. Knowing that spacing, you can figure out these slits per meter or per millimeter. But anyway, let's figure out, based on lambda, let's figure out what D is. Forgive the thickness of my pen. It depends on the zoom level I'm at. And so we wind up with 5 times 10 to the negative 8 meters, 5e negative 8 meters is the slit-to-slit spacing. I know that the relationship between the slit-to-slit spacing and the number of, like, the, I should say, the lines, the meters per line. So that's 5, like, per, meters per spacing. So that's 5 times 10 to the negative 8 meters per line, and I want to know lines per meter, and so that is the inverse of that. And that's what it's looking for, the number of slits per millimeter. So that gives us 2 times 10 to the 7 lines per meter, but it's not a meter size diffraction grating, it's lines per millimeter, because diffraction gratings are kind of small. So we'll just convert from meters to millimeters, and we will have our answer. Of course, there are 1,000 millimeters in a meter, so, and we have just enough space for our answer in the box. 2 times 10 to the 4 lines per millimeter. And that's wrong because I can't do math. So let's backtrack. My reasoning is right, my slope calculation is right, slope equals lambda over d, but d does not equal slope times wavelength. And come to think of it, that's 20,000 lines per millimeter. That's a little bananas. Anyway, but so d is not equal to slope times wavelength. D is equal to wavelength over slope. So let's see. I think I can fix this rather easily. Okay, so that gives us 8 times 10 to the negative 6, so 8 micrometers per line spacing. So we'll put in 8e negative 6 meters per line, and we have to invert that to get the lines per meter. Okay, so 126 lines per millimeter. That sounds more reasonable. Now, I also notice I went from 8 times 10 to the negative 6 meters, and then when I did the lines per meter, I actually used the non-rounded number 7.9125 times 10 to the negative 6. The reason why I have one significant figure here on 8 times 10 to the negative 6 is because the numbers on the graph are only to one significant figure. I guess, I wonder, actually, come to think of it, if the numbers, like something like an index, is an absolute number that has no, there's no issue of significance. But at any rate, the mark scheme says that the answer is 126, 1.26 times 10 to the 2 lines per millimeter. Where they're getting three significant figures from, I don't know. Because there's either one significant figure or the numbers are absolute, and the significance goes all the way out to 126.382306.5 that I'm getting off my calculator. So I don't know where they're getting three significant figures from. I'm not sure they necessarily care. The 4 points that are, in terms of where are the mark scheme points, we have the fact that gradient is lambda over d. That was one point right there. Then actually finding that the slope is 0.08 is the second point. Then figuring out the line spacing, that was the third point, and then the fourth point is actually getting to the answer, realizing that you have to do 1 over the line spacing in order to get the lines per meter, per millimeter. So there we go. All right, believe it or not, we're not actually done with number 3. There's still E and F. So the variation of, on the graph of sine theta versus n, what if you used a light source with a smaller wavelength? Well, the wavelength is related to the slope. We already figured that out. Yes, the slope is lambda over d, so a smaller wavelength means a smaller slope, because they're directly proportional to each other, so the slope would be shallower. And in 3f, increase the distance between the diffraction grating and the screen. So here's the equation for diffraction grating, n lambda equals d sine theta. The distance between the diffraction grating and the screen, that's the capital D, has no bearing in this expression. Even if we did sine of theta over, if we actually laid out, the expression as we saw it over here where sine of theta equals lambda over d times n. Sine of theta equals lambda over little d times n. Still, the distance between the diffraction grating and the screen has no bearing on that relationship, so there would be no effect. And yes, there is the formula, let me look it up. S equals lambda d over d, like the capital D is in that equation, but that's for a double slit situation, not for a diffraction grating. So 3F, no effect. Okay, so here we are with number 4, featuring a thin film. We have magnesium fluoride on glass. So we're going from air to magnesium fluoride to a higher index. Just so a reminder, and under the condition where you go from air into the film and then back out into air or into a lower index, constructive interference is 2dn equals m plus 1/2 lambda, and destructive is 2dn equals m lambda, but we're going from a small index to a bigger index to an even bigger index for the lens, and so the constructive and destructive equations switch, and so we have 2dn equals m plus 1/2. No, it's not m plus 1/2. It switches. Sorry, it's m lambda. Let me fix that. M lambda, and then destructive interference is m plus 1/2 lambda because of the phase changes. And then we have first one, 4A, and yeah, if you're wondering, is the lens actually have a higher index than magnesium fluoride? It says it right there in the problem, lens 1.58. 4A, whether ray X undergoes a phase change. So 4A, does ray X have a phase change? Yes, it does, because it reflected off of a material with higher index, and when that happens, the reflected ray is 180 degrees phase shifted. So there is 4A. It doesn't say so in the description, but the first mark is for yes or no, phase change, and then the second mark is for Y, or at least the amount of the phase change. 4B, state in terms of D the path difference between rays X and Y. Well, Y enters the magnesium fluoride and then reflects off of the lens, comes back through the magnesium fluoride and out again. So that means that ray Y the path is is the same as X, but it has, let's see, goes D across the magnesium fluoride, reflects, goes D again, and then out it goes, and so the ray Y is going to have a longer path than X by 2D. Okay, let's move on. Then we have 4C, calculate smallest value of D that will result in destructive interference between ray X and ray Y. We see the destructive interference is 2dn equals m plus 1/2 lambda, and it says what is the smallest value of D, so that would be starting with an m value of 0. So that's 2dn equals 1/2 lambda. So there's 4C. We have 2dn equals 1/2 lambda. Solve for D. They gave us the wavelength 656 nanometers that was given in the problem. We're given the magnesium fluoride index is 1.38. And so we get 119 nanometers for our value for D. Okay, so 4D says practical advantage of this arrangement. In other words, using this thin film on glass causing destructive interference that would eliminate the reflection. So why would you want to eliminate reflections? And you'll notice that this actually has 2 points to it. So this particular, like getting rid of a reflection, it gets rid of glare, or if you don't want reflections off the front of your lens or glasses to cause glare onto someone else, that this particular setup, this thin film will get rid of that. So that's one point. And the second point is they want you to point out that it is at a particular wavelength, which is true. I mean, 2dn equals 1/2 lambda, and so we're talking about a particular lambda. So at a particular lambda, the glare is reduced. It also says in the mark scheme, and I've also seen this in the notes and in materials, that reducing the reflection increases the amount of energy actually getting to the sensor on the other side of the lens. And I'm not entirely sure why that's true. Why eliminating a reflection would increase the light to the sensor, that would increase transmission. So I'm not sure why the destructive interference eliminating reflected light would therefore increase the transmission all the way through to the sensor. Yeah, I'm not really sure why that's true. My dad was an optical engineer. I should follow up and ask him about that. But at any case, increases light to sensor is not actually one of the necessary points. The one necessary point is the elimination of the reflection, and the other, to get the second point, they do say that they want you to specify that it is at a particular wavelength. All right, 4E. Notice for 4E that they give a new description. It says light from a point source is incidence on the pupil of the eye of an observer. Diameter of the pupil is 2.8 millimeters. So this is a single pupil. So this is single slit. And so 4E, let's actually make a note on that. And then it wants the intensity versus the diffraction angle for a single slit. So we don't want like the multiple bump. We don't want the the kind of thing for two slit. They want you to draw the envelope that is produced by a single slit. So remember, we have our wide central maximum. That should do it. Keeping in mind that the width of the central primary maximum is double the width of the secondary maximum, and that the secondary maxima are much lower than the primary maximum. I should probably make those bumps even smaller. That should be good. And then again, keeping in mind, again, that in terms of the width, that the width of this primary central maximum is about double the width of either of the secondary maxima. And the mark scheme actually says that the secondary maxima should be no more than a fifth of the central maximum. So if you went higher than thank you. If you went higher than this line, if you went higher than that, they would take the point away. Okay, 4F deals with resolution, and that's 9.4, so we're going to skip 4F. All right, let's keep looking. We have number 5, and then 5 is about a sound wave in a metal sheet. We're not actually interested in number 5. I'm not sure why 5 was included, but we don't need to worry about 5. Here's more of 5. No. It's some Doppler situation. And so it brings us to number 6. And number 6, we can see we have a two-slit situation. And so we are on 6A. Okay, so for 6A, it says initially the lower slit is covered and the intensity of light at M due to the upper slit alone is 22 watts per meter squared. And then it says the lower slit is now uncovered. So with just the first slit uncovered, then we have single slit, and we would wind up with the single slit diffraction pattern that shows up. But then by uncovering the second source, we now are going to have a two-slit interference pattern that shows up on the screen. Now, point M is in the center, and so we know that the center of either diffraction or interference pattern, there is a constructive interference that occurs at that point. Okay, so deduce in watts per meter squared the intensity at M now that the second slit is uncovered. Well, it's going to be 4 times 22, so we get 88 watts per meter squared. But this is 3 marks, so the deduce means you have to explain why this is so. So there are a couple of different points here. The first is figuring out that as a result of there being 2 sources now going, and of course we know that M being right central to the slits, that's where the bright central maximum is. But now that we have two sources, we have maximum constructive interference happening at M. So that the notion of the constructive interference happening at M, that is the first point. And then the two crests are going to meet, so that would double the amplitude. So actually, doubling the amplitude, that's still part of the first point. And then we need to remember that the intensity of light is proportional to the square of amplitude of a wave. All right, so that's the second point there. So if we double our amplitude, 2 squared is 4 times the intensity, and 4 times 22 watts per meter squared is 88 watts per meter squared. So that's the third point. So we have 1, 2, 3. There's the third mark right there. So that's 6A. So then 6B says that the point P shown in the diagram, that's the position of the first maximum on one side of M, and it gives the distance between the slits, it gives the distance to the screen, it gives the distance from M to P, that would be lowercase s, the distance to the between maxima on the screen, and it says calculate in nanometers the wavelength of the light. So this is the classic two-slit equation. So let's go to 6b. Here's 6b. So calculate the wavelength of the light. So again, the distance from the centered M to P, that right there, that is from the center maximum to the first maximum, that is S, the distance between the fringes on the screen. So we know that as S. And so we know D, we know capital D, and it wants to know what is wavelength, so of course we do S is lambda D over D. And so that gives us a wavelength of 5.6 times 10 to the negative 7 meters, which is 560 times 10 to the negative 9 meters, aka 560 nanometers. Okay, so 6C says the width of each slit is increased to 0.03 millimeters. Capital D, lowercase d, and lambda remain the same. I want to see if the width of the slits was given to us to begin with. I don't think it was. No, it wasn't. There's only one equation that involves the width of the slit itself, and that goes back to the single slit formula, theta equals lambda over b. And you can see that b and theta are inversely proportional. So for the same wavelength, if I am increasing the slit width, that's going to be tightening the angle. And so it says why the intensity at P will be less by tightening the angle that closes in the single slit diffraction envelope. So yeah, increasing the slit width increases, or it reduces, because they're inversely proportional, reduces the angle of that single slit envelope. So the envelope, that curve, so that curve becomes tighter. You still get the same number of fringes visible under the curve, but by having a tighter curve, it kind of brings the curve downward, so that the intensity or the amplitude of each fringe, each peak, is less. So the intensity at point P would be less because the single slit envelope is tightening, because the slit width is widening. So due to single slit diffraction, now we're on 6D. Due to single slit diffraction, the intensity on the point on this at a point on the screen, a distance of 28 millimeters from M, is 0. So that would be the first minimum. So that's, again, using single slit, we have theta is lambda over b, and theta is the angular displacement to the first minimum when we're talking about single slit. There's the theta in question, from the center line, the angular displacement to the first minimum. And so, beep, what the question is saying is that this side right over here is 28 millimeters. Well, we know the distance from the slits to the screen, that was given. And we know the distance from the slits to the screen, that is 1.5 meters. So we can use tangent of theta is opposite over adjacent, and then solve for theta. So we can figure out that theta is 0.01866667, etc. radians. And then we can confirm if that is the angle that satisfies theta equals lambda over b. We can then actually just use this over here. We have a wavelength. We know that the wavelength is 560 nanometers. That was given to us. Where was that given to us? Let's find 6A. Duh, that wasn't given to us. That was the answer to 6B. They had to solve for the wavelength. All right, so 560 nanometers. I'm trying to finish this problem before I eat lunch, so now I'm hungry and so I'm not focused. All right, almost done. So 560 nanometers divided by B, which is the slit width that they gave to us earlier, right before 6C. So when I divide that up, and so when I solve for that angle, I get to the same number of significant figures, the same angle. And so that checks out. So therefore, yes, the distance from the center line to the position of the first minimum is 28 millimeters. And that's it for number 6. Now, let's see. So 7A deals with energy of a photon, so we're not going to look at that right now. Same with 7B, and then, or 7C. Then 7D deals with the diffraction grating, but that's actually a resolution question, so we're not going to deal with that right now. That's our next topic. Then bring this all the way back over here. Then we have 7E. Calculate the angle between the first order line of the red light in hydrogen and the second order line of the violet light in hydrogen. Okay, so calculate the angle between first order line of red in hydrogen and second order line of violet in hydrogen using n lambda equals d sine theta. Solve for theta. Theta is sine to the negative 1 and lambda over d. So using n equals 1 and n equals 2 for red and violet, the wavelengths were given in the problem. For red and violet, again, we're talking about the hydrogen. So I throw those numbers into the equation, and for red, I get 0.334338 radians. For violet, I get 0.422651 radians. The difference between those two is 0.0883313 radians, and if I convert that to degrees, I get 5 degrees. The mark scheme gives the answer in degrees. I figure you could probably give the answer in either, because both radians and degrees are used to measure angles. So there you have it. Now 7F. So it says light source is changed so that white line is incident on the diffraction grating. Outline the appearance of the diffraction pattern formed with white light. Well, white light is all wavelengths, right? And the formula for a diffraction grating is that n lambda is d sine theta. So this is good, that, white is all visible wavelengths. We have n lambda is d sine theta. All wavelengths, they have the primary maximum at the center. They all have constructive interference there. So you would see each color in the center, and if you're seeing all of the colors in the center at once, that makes white. So the center is going to appear white. But then as you move away from the center, you're going to have a difference in where the maxima are, because the wavelength, oops, that's eraser, not, there we go. Wavelength is proportional to the angle as to where the maxima fall. And so the shorter wavelength, being violet, is going to have a smaller angle. So violet's going to be on the inside, and red with a longer wavelength is going to be on the outside. So the way that would look, I can actually illustrate that kind of sort of using colors. So if we start off with like a dark screen, since all of the colors have primary maxima in the middle would be white. Okay, I want to get rid of these dark screen. You get the point, it's a dark screen. All right, and then, so there's the central maximum, which is all the colors, and of course there's a gap, and then that's the minimum, and then you have blue being closest to the inside, and then you would have like green and some yellow, and so on and so forth. Then you would have a dark band, and then the process would repeat itself and then just keep on going. And then since these are angular displacements, these aren't fixed linear displacements. As the orders go increase, as you get like greater orders, then you would have wider bands. Because the angles are bigger, but you're chopping those angles with a screen that's flat in front of the slits. It's not a curved screen. If it was a curved screen, the bands would not get any wider. But if it was a flat screen, as you move away from the center, the bands would get wider. Yeah, that's a little better. There. So that's already almost, it's past 45 minutes, and I think that's a good start on 9.3 problems, and then there are a few other problems that I will leave to you as a take-home, and then I will record a solution video for those in a second video. All right, thanks.